Okay, it's now recording. So let me just say a couple of announcements. This way we save some time for people who was lost with the links chaos. So yeah, we are starting the second semester of HoloTube. You can check on the web what the talks are gonna be. We will improve the web. These mistakes should be corrected. As usual, the talks are gonna be on Tuesday and mostly at 4 p.m. Central European time. Then about, this is also for you, Mark. Normally the talk is 1 hour, but we are pretty flexible with time. And there's a lot of freedom for people to ask questions. So just whomever wants to ask a question, just unmute yourself and ask a question. If there is too many questions or things are derailing, I will try to moderate. But this is it. And just let me answer some of the organizers which are lost in Skype, like Navid, who but okay, I guess I think we have to start. So yeah, it's very nice, and I'm very sorry about this, Mark. It's very nice to have Mark Mezei from Stony Brook, who will tell us about this very interesting recent work of his and collaborators about policy keeping and chaos. So Mark, please go ahead.
Thank you very much for the invitation and all of you for coming. And let me reiterate that please ask questions, especially that we have a relatively small audience today. So my title will be Pause Skipping and Related Probes of Away from Maximal Chaos. And this is work done with Sharoshi, Choi, and I'll also be mentioning some earlier work with Stanford, Wanda Shi, and Virueta. Okay, so as an introduction, let me remind you that there are a variety of phenomena and signatures associated with quantum chaotic dynamics. The transport of conserved densities, here is diffusive transport. The thermalization starting from an out of equilibrium initial state. The quantum butterfly effect. The recently proposed pause skipping phenomenon, which is proposed to be a signature of chaos, the growth of complexity of states and of the time evolution operator. And historically, the first signature of chaos was investigated in the statistics of eigenvalues, energy eigenvalues. The ultimate goal of this research direction is to describe these phenomena in a unified theory. That's extremely ambitious. Our goal today, or my goal in my research, is to develop effective field theories valid at long distances and late times for some of these processes, and to study their interplay and their relation to gravity through ADS-CFT. So today I'll mostly be focusing on pause skipping, but to put things in context, I'll start discussing transport, some results about the butterfly effect, and in the end, we'll also talk about thermalization to discuss some relations between these phenomena that are emerging. And an overarching theme of the talk will be an attempt to go away from infinite coupling or maximal chaos, where things are relatively better understood. Okay, so as a warm-up and to put everybody on the same page, let me briefly go over one formulation of hydrodynamics, which is an extremely strong and universal description of transport of conserved densities in all chaotic systems. The main physical idea behind it is that at finite temperature, we expect that most excitations relax in a characteristic time, local equilibration time, which in strongly coupled systems is expected to go with beta. If you have a weakly coupled system, then this beta can be divided by a small coupling constant g squared, Even in those systems, if you wait long enough, the system will eventually equilibrate. Now, in the regime where we take wavelengths very long, so p times t log is a lot smaller than 1. In this dynamical regime, the dynamics of conserved densities become slow. They are approximately conserved. Okay, so the next step is to think of hydrodynamics as an EFT valid at long distance, as a systematic expansion and long distances and late times. And the key mathematical step is to rewrite the stress tensor in terms of fluid variables, so the energy density, pressure, and the 4 velocity. And here I wrote down explicitly the 0th order ingredient terms, and I grouped the higher order ingredient terms in this tensor pi. And then the dynamics follows from the conservation of the stress tensor. If we linearize around the equilibrium configuration, we can easily determine Green's functions. This is the Green's function that you get in hydrodynamics for the energy density. You see a sound mode that is linearly dispersing and has a small decay width. Hydrodynamics is not just about the conserved densities. In this effective field theory, you can rewrite any microscopic operator, any operator in the microscopic theory of spin L, is OL, as expressed through the stress tensor. So in this case, we act with L-2 derivatives on the stress tensor. Here I'm not writing in indices. This is just schematic, and there are some coefficients which are not determined from EFT reasoning, have to be determined from matching to the UV theory. And so this would be the leading term, and then there are also polynomials in the stress tensor. And you have to write down any combination that is allowed by symmetry. And if we want to calculate correlation functions of this microscopic operator, what we do is simply do this replacement, use these Green's functions, and we get the systematic long distance late time expansion. Okay. Now I talked about hydrodynamics here, but in this talk we'll also be interested in systems which do not conserve momentum. And in that case, the Green's function of the energy density takes this diffusive form. So let me now discuss the pose of these Green's functions. So let's see. So the dispersion relation of the pole in hydrodynamics, as we said, is a linearly dispersing sound mode. And in systems without momentum conservation, we get a pure imaginary pole on the lower half plane, which is dispersing quadratically. It would be really nice to compute this Green's function in a microscopic theory, by which I mean to get an expression that is valid for all omega and p. If we had that, we could follow the fate of these poles away from the hydrodynamic regime to momenta that are order 1 in this local thermalization time scale. And we would be able to read off all order transport coefficients from such an expression. And this is exactly what we will do when discussing pole skipping. A landmark achievement of ADS-CFT was to compute such a finite temperature correlator at infinite Toft coupling in super Yang-Mills theory by solving differential equations numerically. In some sense, we will do even better in the SYK model. And just a comment on philosophy. So one can imagine an alternative history in which hydrodynamics was not known, and string theory studying bumpy ADS black holes through the fluid gravity correspondence discover some laws that govern transport in super Yang-Mills theory. And a key step would have been to realize that this theory is formulated in variables that are appropriate for any chaotic system. And the bold conjecture could have been that hydrodynamics that was derived from gravity actually governs all chaotic systems. And if history went this way, then string theories would have been correct. We know that hydrodynamics is universal. So this is a useful method of discovery to keep in mind. And this motivates some of my attempts in understanding better the butterfly effect and thermalization. So try to isolate the relevant dynamical variables, try to write laws that could apply to any chaotic system, and then boldly propose that they actually do apply to any chaotic system. Is there any question about this introduction? If not, then this example of hydrodynamics, where I didn't say anything new, will just serve as a motivation for what we are trying to do next. So I will start discussing the butterfly effect in some detail to put context around the main part of the talk, which will be about pause skipping. And if time permits, in the end, I will give some comments on thermalization, and then I will end with a summary and open questions. Okay, so all of us are familiar with the butterfly effect in classical physics, which is the exponential sensitivity to initial data. And in recent years, a lot of work has gone into investigating what the quantum many-body generalization should be and it turns out that the appropriate generalization is to look at simple operators, by which I mean a few body operators in spin chains and low dimension operators in conformal field theory, and evolve them with Heisenberg time evolution and watch them evolve into complex ones. This captures the intuition that the injection of one particle in the system at later times can have an effect on the entire system. Just watching operators evolve is too complicated for the human mind. We need a diagnostic, which is a number. And this diagnostic turns out to be the out-of-time ordered commutator. So let me explain to you what motivates this. So we are interested in how the support of the operator V grows in time. So this is a local operator that we inserted at the origin. And we can detect the support of this operator. So this operator grows in time, and we want to detect where it has grown by taking its commutator with another local operator at the space-time point t and x. If this commutator, if the two operators commute, that means that the operator V hasn't spread to that point. But if they do not commute and this commutator is not zero, then we want to pick this signal up. Now, the commutator of two Hermitian operators is anti-Hermitian, but has an undetermined sign. So it makes sense to square this thing and put a minus sign to get a positive expression. This is still an operator. We want numbers. So we take the thermal expectation value of this quantity and normalize with the norms of V and W. And this is a diagnostic of how the operator V grows in time. If we expand out the commutator, it will contain both time-ordered and out-of-time ordered pieces. So by the out-of-time ordered piece, I mean W of t, V0, WT, V0. It turns out that the out-of-time ordered pieces are the interesting ones. Okay, so why is this related to the classical butterfly effect, you may ask. If in semi-classical systems, if we take W to be Q, T, and V to be P at 0, and replace commutators with Poisson brackets, then it turns out that C becomes dq t dq at 0, and that's because the momentum is represented as derivative with respect to q squared. So in a semi-classical system, this would grow exponentially as with 2 lambda L, where then lambda L is this classical Lyapunov exponent. Okay, I'm here assuming that all of you have seen one discussion of this or another. My purpose is only to remind you of things, but if that's not the case, then please ask me questions. Okay, so let's look at how this OTOC looks like in space-time. So here's a diagram. It vanishes exactly outside the light cone. And then it's inside the light cone, it starts small, but then it has a very, very sharp profile in examples, and it saturates to its maximal possible value inside the cone region. This cone region is narrower than the light cone, and its slope determines the butterfly velocity. So the butterfly effect is, we think of the butterfly effect as spreading ballistically with this velocity. Okay. It was found in ADS-CFT calculations that this OTOC is suppressed by 1 over n squared, just like a 4-point function should be in holography, but it grows exponentially in time and decays exponentially in space. This indeed defines a cone-like profile for the OTOC. This result is valid in a hydro-like regime where we go to times and distances a lot greater than beta, but a lot smaller than the scrambling time that you can simply see from here when the exponential growth in time overcomes this 1 over n squared suppression, and then the whole 1 over n expansion breaks down. So you shouldn't extrapolate this answer beyond times of log n when this expression becomes order 1. Okay, so that's the holographic answer. Madasena, Schenker, Stanford showed that this OTOC cannot grow faster than exponentially in any chaotic system. And in systems where it starts small, it can grow exponentially with a characteristic Lyapunov exponent, and this Lyapunov exponent is famously bounded by 2 pi over beta, establishing the result that black holes are the fastest scramblers of quantum information. If we are interested in the growth of the OTOC, not just in time, but in space, then these authors proposed that it makes sense to look at how it grows along rays of constant velocity. So here's a ray of constant velocity. V is that velocity. If we look at this function of 2 variable along such a ray, then we get exponential growth with a velocity dependent Lyapunov exponent that I will denote by lambda of V. With Sharoshi, we showed that this lambda of V obeys a refined chaos bound, which I'm writing here, and which on this plot is the dashed orange line. So it starts from the MSS 2 pi over beta chaos bound and goes down linearly and vanishes at the butterfly velocity, which determines where the OTOC doesn't grow anymore. A remarkable feature of this lambda of b in generic systems is that while it starts out from a non-maximal value as a function of v at a certain critical velocity v that I denote by v star, it reaches the bound, and from then on until the edge of the butterfly cone, it saturates this refined chaos bound that we derive. And so in some sense, in the sense of velocity-dependent refinement of chaos, many systems are maximally chaotic near the edge of the butterfly cone. Okay, how do I know that? So just to make one thing clear, holography would give you a linear velocity-dependent Lyapunov exponent, which saturates the bound for all values of v. Okay, so how do I know that this is the generic behavior? Let me introduce the workhorse of this talk, which is the SYK model. And here I will be using the spatially local generalization of the SYK model. So again, I'm assuming that everybody has seen the SYK Hamiltonian that would be describing the physics of one of these white squares on my figure. I don't know why my pointer is not working, sorry. Okay. So the Hamiltonian is obtained as follows. We choose all groups of Q fermions that are possible and multiply them with a random coefficient in the Hamiltonian that is drawn from an ensemble which has zero mean and J squared variance. Okay, so then to get the spatial local version of the SYK model, we put many SYK models next to each other. So far, they are not talking to each other. And then I add the following term to the Hamiltonian. I take Q/2 fermions from one group, and then another Q/2 from the nearest neighbor. And again, I create, I give them a random coefficient and then add them to the Hamiltonian. This way, I get the nearest neighbor Hamiltonian, and on each lattice site, I have a separate SYK model. So in usual discussions, Q is chosen to be 4, but nothing changes if I change, if I increase Q. I mean, the same physics remains. But at large Q, I have an enhanced solvability of this system. So let me just sketch why that is. So SYK is solvable because after averaging over disorder, you had a collective field description of it, which is usually called G sigma variables. And this collective field has an action that has a n in front of it. And so you can use semi-classical methods like saddle point approximation to solve it. So this large Q limit of this SYK chain has the following effective field or collective field description. It's a local Lagrangian in 2 times, and the dynamical variable is this little g, and there is one dynamical variable for each lattice site. It has a normal kinetic term written in light cone coordinates and the Liouville self-interaction. And the different lattice sites are coupled again through an exponential interaction. This is something reminiscent of Toda theory. But what is this little g in terms of SYK variables? So here are the SYK fermions. I formed bilinears of them. That's where the 2 times come from. Average them over all fermion flavors. So this is an SYK expression. And this is equal to the free fermion propagator times a correction, 1 plus 1 over Q. And here, this is the definition of little g. You can derive this effective action by some Hubbard-Stratonovich. So little g is to be thought of as a fermion bilinear in the original SYK variables. And since this action has a large coefficient, we can find the saddle point. That will give us the fermion propagator, as you can see from this equation. And by linearizing around this saddle point and determining the 2-point function in terms of little g variables, I can obtain the 4-point function of fermions. And this is what we done, and independently Stryker has obtained the same expressions for one SYK dot, where we obtained a closed form expression for the 4-point function for all values of the temperature. Something I forgot to say is that SYK at finite Q is solvable in the low temperature strongly coupled limit, whereas this large Q SYK is solvable for all temperatures and so for all couplings. The dimensionless coupling of this theory is usually called beta J, and I will conveniently instead use just a redefinition of the coupling, little g, which interpolates between 0 and 1. 0 is the free limit, this is the high temperature limit, and g goes to 1 is the low temperature maximally chaotic limit. So in summary, sorry, it was a bit muddled. So the main point that you should take away from this slide is that this small modification of SYK allows us to go away from the strongly coupled maximally chaotic limit and still be able to solve this model. And this will give us a lot of mileage. Okay, so let me show you how we obtain the velocity-dependent Lyapunov exponent, lambda of v in this model. So going through all those steps that I mentioned, for the growing piece of the 4-point function, we get the following simple expression. So P is just the spatial momentum, and from every momentum mode, we get exponential growth. There's a plane wave part, and there's an important denominator that will play a role. Lambda of P was determined in this recent work of ours. For all values of the coupling, it takes this form. So as we change G, we interpolate between a free and maximally chaotic theory. Now we are interested in the OTOC in the hydrodynamic regime. So for times greater than beta and a lot smaller than the scrambling time. And there we can evaluate this integral using saddle point. So here I'm already imagining that I set x equals v times t. So I have just t to tune. For small v, the saddle is on the imaginary axis. The original contour of integration was on the real axis. We'd have to deform the contour into a steepest descent contour, pick up the saddle point value, and we are happy. And lambda of v that we are looking for turns out to be the Legendre transform of lambda of p, which I wrote here explicitly. Okay, as I increase v, this saddle point goes upwards on the imaginary axis, and it may cross a pole. This pole is coming from this denominator becoming 0, so namely lambda of p becoming 1. So it's clear that if this is 0, then you get a pole. And so at v equals v star, the saddle crosses the pole. And if we go for v's that are bigger than v star, then the saddle is sitting here. If we want to deform the contour of integration from the real axis to go through the saddle, we necessarily pick up the pole contribution as well. And it turns out that the pole contribution always dominates. The pole is accounting for the stress tensor contribution to chaos. And in this case, it always dominates the answer. And so that's the mechanism by which for v greater than v star, we get some simple expression, some linear lambda of v, which is coming solely from the stress tensor. So let me show you a concrete expression. So first, let's look at relatively strong coupling. For v smaller than v star, you see a curving plot This is coming from the Legendre transform. And after V equals V star, we get just a linear dependence. And the butterfly velocity is determined by the stress tensor contribution to it. If we go to small coupling instead, we get a forever curving plot. So in that case, we are always in this situation. And the butterfly velocity is smaller than what the stress tensor alone would give you. Okay. Similar results can be obtained for conformal theories on hyperbolic space. This includes 2D CFT at finite temperature, where the role of lambda of P is played by the leading rigid trajectory, where the rigid trajectory is the spin of the operator as a function of its dimension, which is known from integrability in n equals 4. If you analyze it, you see that for Toft coupling greater than 37.7, you are in such a situation, and below that, you are in this situation. So in this case, if you go with V between V star and VB, then you are dominated by the stress tensor, and you get in this refined sense of chaos, maximal chaos, whereas if you are at small velocity, you still see that you are not maximally chaotic. Only in the infinite Toft coupling limit do we get maximal chaos for all values of the velocity. And it's an interesting direction is to try to write down an EFT for this OTOC, which is understood in the case of strongly coupled SYK, where you get the Schwarzian theory, which is a time reparametrization pseudo-Goldstone boson, and which is the boundary graviton of the dual JT gravity. And what we are working on is to go away from maximal chaos and get an EFT there. And our workhorse is this SYK model. Is there any question about this? If not, let me go on to discussing pause skipping. Okay, I see I'm already halfway into the talk, but we needed this introduction and giving context to be meaningfully discuss pause skipping away from maximal chaos. So let me recall from the hydro discussion that in the retarded energy 2-point function, we have a family of pores that start their lives either as a sound or an energy diffusion mode. Now, in the strongly coupled limit of SYK, it was computed in the early papers that this correlation function takes the following form. So we get the formula that we wrote down in hydrodynamics with a small modification that in the numerator we have 1 plus omega squared. Of course, in hydro you would drop this omega squared piece, but here we want to go beyond hydro. Now you can see that this family of poles continues exactly quadratically forever, but at omega equals I, we have that the residue of this pole vanishes. And the corresponding P is I over square root of D. So some funny phenomenon is happening. This is what's called pause skipping. You have a family of pores, and as you go along that family of pores, at a special point, its residue is vanishing. In this case, this special point can be rewritten in terms of data of chaos. I'm working with beta equals 2 pi. So in these units, lambda L is just 1, so I can introduce that here. And 1 over square root D is 1 over the butterfly velocity in this special model. Of course, you could dismiss this as a silly rewriting, but it turns out that in ADS-CFT, you get the same phenomena, namely that at this exactly at this special point, pole skipping happens in the energy density 2-point function. Well, let me say a couple of words about how that comes about. So as was shown in these papers, at this special pole skipping point, one of the Einstein equations one component of the Einstein's equation trivializes, and this leads to an ambiguity in the Green's function as computed from the ratio of the two different fall-offs of the near boundary behavior of the metric. So, I mean, probably all of you know that this is to be interpreted as the source and this as a wave, and this is how we compute Green's functions in holography. So we have two independent fall-offs near the boundary, and they get tied together by boundary conditions in the path. In this case, in the case of retarded Green's function, the infalling boundary conditions on the horizon. The poles come from the zero of this source term corresponding to normalizable modes in the Bach, and the zeros of the correlator come from the zeros of B. At the pole skipping point, so one way of saying what happens in the pole skipping point is that the Einstein's equation trivializes. Another way of saying it is that while for generic omega and p, we have one infalling mode. At the pole skipping point, both modes are infalling, and so you have an ambiguity. You don't have the boundary condition doesn't determine for you what's going on. So, in summary, okay, so the motivation for looking for this point, so why are we interested in this point, is that this OTOC that I talked about is a very complicated observable, and it would be nice to tease out data of chaos from something simpler. And indeed, these authors have found that there's a subtle signature of chaos in the energy density 2-point function. Something funny, namely this pole skipping behavior, is happening at this special value. The residue of the hydropole vanishes at this special value of omega and p. So this has been this phenomenon has been tested as I reviewed in ADS CFT, in the strongly coupled SYK chain, and in stress tensor dominated CFTs on hyperbolic space. And it's also explained by the EFT for maximal chaos of Blakely-Liu. With Choi and Sharoshi, we asked, what could be the non-maximal chaos generalization? So already from what I told you, we can make an educated guess. It is well known that the stress tensor 2-point function is universal in CFT in flat space. And via transformation, we can make this into a thermal system living in hyperbolic space at some special temperature. This includes 2D CFT at finite temperature on the straight line. We know that while this is universal for all CFTs, not all CFTs are maximally chaotic. For example, the free scalar has 0 Lyapunov exponent. We also saw in the previous section that the butterfly velocity in weakly coupled theories is generally smaller than what the stress tensor tells you would be. So from all this, we came up with the proposal that the pole skipping point should really happen at I times 2 pi over beta, 1 and 1 over the stress tensor contribution to the butterfly velocity. Just a couple of comments about the pole skipping point. So as I emphasized, this is outside the hydro regime. We are working with momenta and frequencies, which are order temperature, whereas the hydro regime would be a lot smaller than temperature. And also we are working at analytically continued momenta, so imaginary momenta, whereas in conventional physics, we take real momenta. And this causes, this allows a pole to be on the upper half plane, whereas for physical momenta, the pose of the Green's function have to be, retarded Green's function have to be on the lower half plane. Okay, so after these comments, so we have let me discuss how we justify this proposal. We will use our workhorse, the large QSYK chain, to test this proposal, to provide very stringent test of it. So here's the proposal. Here's the collective field description of the SYK chain that I introduced in the previous section. We have to find the saddle point and then linearize this around this saddle point and determine the 2-point function in the little g variables, which will give you the 4-point function in the fermion variables. Okay, so don't be intimidated by this formula. I just want to highlight some aspects of it. So the linearization around the saddle point gives you a quantum mechanical problem, a simple particle moving in a Peschel-Teller potential, which is 1 over sine squared. And the eigenvalue, energy eigenvalue is related to the center of mass Fourier mode in these 2 times, whereas theta is the difference of the 2 times. We can construct Green's functions of ODEs by finding the 0 modes of a homogeneous equation and then patching these 0 modes. So it is a 2nd order equation. There will be 2 0 modes. We patch them together, and then that introduces a kink. And this kink gives us the delta function in the Green's function. Okay, so what are the 0 modes? One, if we distinguish them by symmetry properties under reflection, we have an even and an odd 0 mode, and both of them are some hypergeometric functions of this spatial variable theta. Okay. So you don't have to remember the details. Now, why are we after a 4-point function? After all, we want to compute the 2-point function of energy density. Our way of extracting this is that we take the OP limit of 2 fermions colliding and extract the energy density, which is a composite operator from fermions from this OP limit. If we go through these motions, we finally obtain the Matsubara Green's function, the Euclidean Green's function, which at even values of the Matsubara frequency n is simply this even 0 mode that I described here, and taking its logarithmic derivative and evaluating it at some special value of theta. Whereas for odd values of n, we get the odd 0 mode of this equation. So this determines in closed form the value of the Euclidean Green's function. But we are after the retarded Green's function. So how do we obtain the retarded Green's function? This is a very hard problem in complex analysis. We are given an analytic function at integer values on the imaginary axis. And we are looking after the unique analytic continuation of this that decays for large omega away from the imaginary axis. There's a theorem called Carson's theorem, which says that such a continuation is unique, but it does not give you an algorithm how to construct it. And here we are facing the following problem. We have a very different expression for even and odd values of n, so it's unclear how to unify them and then analytically continue in n. So we spent quite a bit of time with this problem and eventually came up with a solution. So it turns out that you have to take the linear combination of these 2 0 modes in a way that for integer Matsubara frequencies, you recover these formulas, and to choose these coefficients such that you get a well-behaved function on the whole complex plane. It turns out that these CE and CO coefficients are ratios of 4 gamma functions times some trigonometric functions, and it involved a lot of guesswork until we arrived at the final expression. But the final expression is very elegant. We just need to unify these two hypergeometric functions with these coefficients, and then use the same formula, namely take the logarithmic derivative, evaluate it at a special point, and then to get the retarded Green's function, we plug in n equals I omega plus epsilon. So we're coming from the upper half plane onto the real omega axis, just like we usually do in thermal physics, and that gives us the retarded Green's function. Okay, so we have a closed form retarded Green's function for all values of the coupling. And now we can test pause skipping away from maximal chaos. We can do this analytically, but it's more fun in the talk to show you some plots. So here I chose imaginary P, imaginary omega. The bright colors are indicating where the absolute value of the function is big, and the blue is where the function is small. And you can see that we have a line of pause which starts its life as a diffusion pole, intersecting with a line of zeros exactly at the point where we predicted it. Here I zoomed in. You see the line of pause, line of zeros intersecting at this point. You can also see intricate behavior on the lower half plane with pause skipping points all over. We also analyze this in the paper, but I won't discuss it any further.
Mark, may I ask a question?
Yes.
You write down this is interaction strength G is 0.6, but is this in the regime of maximal chaos or is this in the regime of non-maximal chaos?
This is in the regime of non-maximal chaos. Only G equals 1 is maximal chaos.
Thank you.
Okay, great. Yeah, so so the large QSYK is great because we have this additional knob that we can tune, and only in the G goes to 1 limit do we get maximal chaos. So it's like the Toft coupling in super Young-Mills. Okay, so now that we have a closed form analytic expression for the retarded 2-point function, we can also do what I previewed in the introduction. We can analyze dispersion relations of pause to all orders in derivatives. And here I'm showing you 3 values of the couplings. Sorry, this V is supposed to be G. The first 3 pause, how they disperse. So this is the hydropole at different couplings, and you can see that it collides with a non-hydropole at some value of P. And following these very interesting papers, we can analyze the convergence radius of hydrodynamics and so on by having this explicit expression. So let's take stock what we have achieved. And nowadays, if you don't have an opinion, you can go on Twitter and go away with an opinion. So let's do that. Okay, it starts good. It says this paper today is brilliant. Okay, so as far as we know, this is the only expression of its kind. We usually are stuck at weak coupling or extremely strong coupling if we use holography. Very happy to learn that we can interpolate between the two, even in this dirty finite T setting. So to summarize, I think that this formula can, besides the applications I've already shown you, I think it's worth thinking more about what one can do with such a formula. And probably we haven't extracted all the physics that is there in this Green's function. Okay, so let me summarize what I talked about so far. So after hydro, we talked about the velocity-dependent Lyapunov exponent lambda of V. I showed you that at strong coupling, typically we get a graph like this. At weak coupling, we get a graph like this. And lambda of V obeys a refined chaos bound. We discussed some explicit examples, mostly in SYK, but also in holography. Then we proposed a pause skipping point where the pause skipping phenomenon should happen away from maximal chaos. So pause skipping still happens, but it happens at this point. We don't have a proof of this away from maximal chaos. We just have one strong example, which proves the consistency of this proposal. So the pause skipping point captures the stress tensor contribution to chaos, which for velocities between V star and VB indeed controls chaos. But let me emphasize that just having pause skipping does not lead to is not a good signature of chaos, because the contribution of the stress tensor to chaos can be decreased by other contributions or even completely cancelled in the case of the free scalar. I think our work demystifies pause skipping, since the energy density 2-point function and the stress tensor contribution to the butterfly velocity are both properties of the stress tensor. It's not so surprising that they can show up in the same formula. But the stress tensor alone does not know about the Lyapunov exponent, and so it cannot be that the Lyapunov exponent shows up in the pause skipping formula, and indeed it does not. And as I emphasized, we have a closed form thermal Green's function that allows us to demonstrate many interesting phenomena, and probably there are some things to uncover. Okay, in the remaining 10 minutes, if I
Can I ask a clarification about the statement on the previous slide?
Yeah.
So lambda L here for you is 2 pi over beta. And your bullet point about demystifying pause skipping, by this you mean that omega PS is lambda L and not lambda V. And lambda V is the Lyapunov exponent.
Okay, yeah, so lambda, lambda L, which is conventionally called the Lyapunov exponent in the literature, is lambda at V equals 0 in my notation. And I'm saying that the omega at the pause skipping point is simply 2 pi over beta, which has nothing to do, which in general is not equal to lambda L.
Okay, thank you.
At maximal chaos, it's of course equal to lambda L, but it's not very informative, because if we know that we are at maximal chaos, we already know the Lyapunov exponent.
Okay.
What is interesting, so what is a diagnostic of chaos here is that this butterfly velocity from the stress tensor is indeed something that is a non-trivial, has non-trivial dependence on what theory we are looking at, and that's indeed a data of chaos. Whereas I would say that 2 pi over beta is not a data of chaos. In the case of maximal chaos, of course it is, but in general it is not. Or you can say that it's the stress tensor contribution to the Lyapunov exponent. So you can, I guess you could say that this guy is lambda L of the stress tensor. That would be a correct thing. And in that sense, pause skipping is giving you the stress tensor contribution to chaos. But unfortunately, these contributions don't add up. They can be decreased or completely canceled. Thanks for the question. Okay, so in the remaining 9 minutes, let me just very quickly
brief comment that
yeah.
The computation is beautiful, and the statement that VB sits in the stress tensor is very nice, but in weakly coupled theories that are perturbatively described by the Boltzmann equation,
okay,
we know that the energy correlation function actually knows very well about lambda L also after an analytic continuation. So the stress tensor does not know about the Lyapunov exponent is explicitly not so in any weakly coupled theory. So I think the interpretation about demystifying, I would say actually it mystifies pole skipping even more, because by your own introduction, it's a very natural in objects that are maximally chaotic precisely with lambda L is 2 pi over beta. But the fact that you now have an example which shows that this is also the case when you're not have maximum, it makes it actually rather mystifying. So my guess at the beginning would have been is that the moment you go away from maximal chaos, you will not find pole skipping. So it is beautiful, but I would say it makes it more mysterious.
So are you, just to clarify what you're saying, maybe I should have looked at your work more. So are you saying that in kinetic theory, pole skipping happens at the value of the Lyapunov exponent?
No. There's no pole skipping as far as we know. I mean, this is still an open question. There's no pole skipping that we know that happens in weakly coupled theories. Nevertheless, from the stress tensor, well, not directly from the stress tensor correlation function, but from the Schwinger-Dyson equation that determines the stress energy correlation function, I can extract the Lyapunov exponent from you.
I understand. Okay. I don't have anything to say on this because I haven't looked at this literature, but I would be very happy to discuss it afterwards. Okay, so then if we incorporate Conrad's remark, then I guess what he's saying is that there are still some mysteries, and there are some examples where this relation, where our proposal does not seem to be true. Okay.
I don't know. I don't know. My guess would have been that it would not be true. So the fact that you have an example is fantastic.
Okay, great. But you're okay. But his point is that the stress tensor knows about the Lyapunov exponent in his weakly coupled example. Okay, that's a very nice point. Thank you very much. Okay, so very good that we have a discussion. So I'll just rush through this part of the talk. I didn't plan to spend too much time on it. All I'm saying is that one nice setup where you can study chaotic dynamics, which is distinct from what we have been discussing, is very much out of equilibrium, where we start from an out of equilibrium initial state and study how it thermalizes, and we can probe this with entanglement entropy, which probably most of you are familiar with. So we take a geometric subregion and that provides coarse graining, and we can watch how the entropy evolves from a low value in an out of equilibrium sparsely entangled initial state to the thermal value. And there is a hydrodynamic regime that is worth spending some time with. So here's a sketch in spacetime. The purple plane, why is my pointer not working? Okay, anyway, so this plane represents the initial state, and then we are interested in the entropy at some later time. So this gray plane is a time slice. This is the subregion with linear size r, and we take both the time and this size r to be fixed and large, a lot larger than the local equilibration time, which we said is order beta in strongly coupled system. And so this is a hydro-like limit. In this limit, the entropy is expected to be more universal than away from this limit. It has an extensive prefactor times a scaling function that only depends on the ratio of time with r. So this is the leading piece. There are sub-leading pieces. T over r is what we keep fixed in this limit. Okay, from these very nice works, we understand the qualitative picture of what should be happening. At early times, we have a long, parametrically long regime of linear growth. Then at some finite time, we saturate to the thermal value. The increase of entanglement entropy in itself does not detect chaos, just like in pause skipping, but its dynamics is universal in chaotic systems, and we can learn a lot. Now, I've done a lot of work on this topic in this hydrodynamic limit. One can determine an effective theory, just like hydrodynamics for this process. And this effective theory can be derived both from holography and in the condensed matter literature, it was derived from random quantum circuits. So there's a remarkable unification between condensed matter and high energy approaches, since they lead to the same effective description. In this alternative history, thinking about this problem, this would be considered a very strong indication that this is indeed universal for all chaotic theories. I don't have time to explain to you what this effective theory is. I'll just show you one of its predictions, that for spherical regions.
Mark, sorry, just let me tell you that, I mean, take it easy with time. I mean, you don't have to.
Sure, but anyway, I was planning not to go into too much detail. If people want, in the end, and ask about it, I can explain what.
Yeah, that's a good idea.
Yeah. Thank you very much. Thanks. Yeah. So I'm just emphasizing that okay, you can derive the entropy evolution from this effective theory. You get this red line for a spherical region, and you get saturation at the value r is the radius of the sphere divided by the butterfly velocity. So the reason why I included this part in the talk is to show that the butterfly velocity shows up in entropy dynamics as well. With Stanford, we gave very general arguments that the saturation time has to be greater than R over VB in any consistent quantum system. And so this saturation, which actually doesn't just happen for spheres, it also happens for elongated shapes, which we showed with van der Schie, leads to the result that black holes are not only fast scramblers in the sense of OTOC, they also saturate entanglement entropy the fastest possible in quantum mechanics. So that's another task that they excel in. Okay. Great. There's an interplay between this effective field theory and hydro, which is way beyond what I can discuss today. So let me summarize and end with some open questions. So we started with discussing hydro as an EFT, as an aspiration. Like if we could achieve that level of understanding for the other phenomena, we would be extremely happy. But we also needed it because it has non-trivial interplay with pause skipping and also with entanglement dynamics. And then we went on to discuss the butterfly effect and to understand what this butterfly velocity really is. And I showed you a refined chaos bound. Then we proposed this pause skipping happens in the energy density retarded Green's function at this value, which should be thought of as the stress tensor contribution to chaos. So maybe I should have said that this is the stress tensor contribution to the Lyapunov exponent. And finally, I'll mention some results about entropy dynamics, which is another chaotic phenomenon. I did not talk about other signatures, for example, the statistics of eigenvalues. It would be really fascinating to relate all these phenomena together. So just to re-emphasize the role of the butterfly velocity, the butterfly velocity delineates the region where the OTOC grows and where it saturates from the region where it stays small, and is often determined by just the stress tensor alone. it shows up in pole skipping, and the butterfly velocity also shows up in entropy dynamics, and one clear signature of it is in the saturation time. Okay, so some open questions, and we'll end here. So one question that excites me is whether we can work out an EFT for OTOCs. This was already done in the strongly coupled limit of the SYK model, where it's the Schwarzian, but we want to understand it away from maximal chaos, which would in the holographic duo correspond to some stringy gravity. Okay, this is, I mean, more ambitiously, we would like to get an EFT for all these phenomena, and the regime of validity should be in some kind of hydro regime where things are more universal than away from it. Blakely-Liu, in the maximal chaos case, have managed to unify pole skipping with OTOCs, but this remains to be done away from maximal chaos, and entanglement dynamics should be part of the story. Okay, these are open. Okay, I'll just leave these questions because the others are about entropy dynamics and I didn't talk much about it. So with this, I would like to thank you very much for your attention.
Thanks a lot, Mark. Very nice. Very nice. We had some questions, but here, of course, we always have time for questions and discussion. So,
can I ask a question?
Of course.
Hi, Mark. Thanks for the talk.
Hi.
You may have already answered this and I missed it, so sorry if you did, but could you say a bit more about this stress tensor contribution to the butterfly velocity? Is this kind of is this coming from calculating certain diagrams in the 4-point function, or what exactly?
No, yeah, so very good. So you are pointing out correctly that it's a little bit of stretch I mean, it would be nice to understand this better. So what I really mean by this is that there is a pole in formulas. So we had this expression, and I attribute the existence of this pole to the stress tensor. And it's the data of this pole from which you can read off this quantity VBT, and see that if you just have that pole, then what you get is a linear contribution. So you have this pole above V star, and you get a linear contribution to lambda V. And if you extrapolate it back to V equals 0, then it would be at 2 pi over beta. So this is what okay, so how do I know that this is actually coming from the stress tensor? And in the SYK context, I cannot give you a very convincing argument. In the case of conformal field theory or conformal Reggie theory, it's extremely clear that so the structure of the OTOC is the same in CFTs in hyperbolic space. And there we really know that this pole is coming from the stress tensor. So there's a special contribution from the stress tensor, and it is what causes this pole. So that's my answer. That we understand where the pole is coming from in conformal field theory, and we see the same pole in SYK. So we think that it's the stress tensor.
Okay, thanks very much.
Thanks, Richard. Any more questions? Comments?
Sorry.
David?
Daniel, I have a question. Yes. Hi, Mark. Thanks for the talk. I have a question about shift symmetry. What can we say about the relation between shift symmetry introduced by Blakely-Liu and your very interesting example away from maximal chaos regime?
That's a very
Is
good.
there...
Yeah, that's a very good question. So Navid's question is that Blakely-Liu have a shift symmetry in their EFT that is used to ban or get away from exponential growth in time-ordered correlators. So that's what protects time-ordered correlators from exponential growth, which they shouldn't exhibit. Since we do not have an EFT away from maximal chaos at the moment, we do not know what replaces that shift symmetry. But one thing that, so it's in the literature, in the published literature, it is not said that Blakely-Liu only applies to maximal chaos, but in unpublished work that was shown by Blake and Liu, that their framework only works for maximal chaos. So we do not know what's the appropriate generalization. And here I commented that that we are working on trying to get such a generalization, and our workhorse again is the SYK model, where we have where we can go away from maximal chaos and have an explicit 4-point function to reproduce. So we're trying to guess what the EFT would be.
Thank you.
Any more questions for Mark? Okay, if not, well, anyway, I will stop the recording. In the meantime, people can still decide to ask questions.
Thank you.
Maybe without recording there.